In this video, we're going to look at two-dimensional projectile motion. And the way we're going to go about it is we're going to deal with the two dimensions as a parametric equation. So x of t equals y of t equals. And in order to start off, our problems are going to usually give us a starting speed, and an angle of elevation. And so what's going to happen is I have some velocity vector that is going an angle above, or I could have sort of below the vertical, depending on how it's thrown. The work will be very similar for both. Here's the problem, though. In projectile motion, if I ignore air resistance, the horizontal and vertical motion behaves very differently. So I need to get to the component vectors. So if this here is the initial velocity, v0, in order to get the initial x velocity, so v0 x, and the initial y velocity, v0 y, I'm going to need to do a little bit of trigonometry. So we can see that this right here, what I've drawn, is a right triangle. Horizontal and vertical are perpendicular. And we're given the hypotenuse. If I want to find the adjacent side, that will be the speed, so like the hypotenuse, times the cosine of theta, because it is adjacent over hypotenuse. And to find the vertical, the v0 y, that's the opposite side to my angle, so that will be the starting speed multiplied by the sine of theta. Now, I guess I'll show it. I can show it here, may as well. The rationale is because the cosine of theta will equal v0 x over v0. No, sort of magnitude-wise. And multiply both sides by v0, you get this. The sine of theta, being opposite over hypotenuse, will be v0 y over v0. And multiply both sides by v0 here, and you get this equation. From here, we can get our parametric equation. So for our purposes, the horizontal motion is going to be, the velocity is going to be constant, so x of t will equal the initial x velocity times t, distance equals rate times time, plus the initial x. And for most of our actual problems, we're going to make this 0, but for some, there could be a point where I might want to consider that I'm starting horizontally at some distance from something. And y of t will be, and since I'm going to deal with just meters and seconds here, so I'll have negative 4.9 t squared plus v0 y t plus y0. And for many of for the example I give you here, y0 will start at 0 because I say it's going to start from the ground. But if I'm sort of thrown from different levels or launched from different levels, then perhaps the height might be a little bit different. So this is going to be critically important to our problems. The problems could be in a few different things. So I could ask for how long the projectile is in the air, how far the projectile goes before it hits the ground, how high it gets, ending speed. There's some other things I could do, but these are some common questions. And basically, the flight time, we're going to find out by seeing how long it takes to hit the ground. So you will set y of t equal to 0 to find when it hits the ground. The range, well, you want to know how long it goes before it hits the ground distance-wise. We can get the flight time, I sort of note that as TF, from this. So the range is going to be how far horizontally we go before we hit the ground. To find the maximum height, we need to maximize a function. We need to maximize y of t by finding the critical points. And for this, since it's a quadratic, you're going to take the derivative and set it equal to 0. Then this will tell me the time that it gets to the maximum height. So then you substitute that t into, not that y, sorry, that t into the height function, because this t will be the time to the maximum height. To find out what that height is, I put it into y. And finally, to find the ending speed, I'm going to use the component velocities. So take the x velocity at the ending time, the flight time, and take the ending y velocity at the flight time. And this will make another vector for us, another set of component vectors. The speed will be this hypotenuse. So this was Vx, Vy. And so I'll just do Pythagorean theorem. Square them and add them, and take the square root. Now, if you're wondering, because I didn't put this up before, the velocity, of course, is the derivative of location. So this is x prime of t. The velocity of y is y prime of t. And these are the common questions, but there could be more, just sort of understand what's going on. Let me show an example that goes through each of these to make sure that we understand how to do them. First example, and all the examples are going to be this rock launched at this speed at this angle. What's going to change is what it tells me to do. So a rock is launched from the ground with an initial speed of 98 meters per second at a 30-degree angle of elevation. Write the parametric equation that models, that's right, equations that model this problem. Okay, so in here, from the ground means y naught is 0. There's no point in saying x naught is anything different than 0 in this problem because it doesn't matter where I start this. So I'm going to draw a little diagram. You don't need to draw the diagram once you get it. This magnitude here is 98. This angle here is 30 degrees, which means V naught x is going to be 98 cosine of 30 degrees, and V naught y is going to be 98 sine of 30 degrees. The sine of 30 degrees is 1/2, and half of 98 is 49. The cosine of 30 degrees is root 3 over 2, and root 3 over 2 times 98 is 49 root 3. So these are my initial x and y velocities. That means that x of t will equal 49 root 3 t, measured in meters per second, and y of t will equal negative 4.9 t squared. This is always going to be in here for meters per second because it's the acceleration, it's half the acceleration due to gravity on Earth, plus the initial y velocity, which is 49, so 49t. And since I'm from the ground here, plus 0, I don't even need it, it doesn't change anything. So there are the parametric equations, and I'm going to use these in the following problems. So here's my next problem. I want to find the flight time. We will recall that x of t was 49 root 3t. y of t was negative 4.9t squared plus 49t. And to find flight time, I figure out when we hit the ground, which is when y of t equals 0. So I'll set negative 4.9t squared plus 49t equal to 0. And probably the easiest way to start this off is to factor out a t. It's a quadratic equation, so I can factor it. And I get t times negative 4.9t plus 49 equals 0. Using the zero product property, either this equals 0 or that equals 0, because the product of two things being 0 means one or the other is 0. So either get t equals 0 or negative 4.9t plus 49 equals 0. This right here is the starting point. We were launched from the ground, so it starts at time 0 at the ground. So that's not my flight time. That's just where I started. And if I solve this, I'll add 4.9t to both sides and get 49 equals 4.9t. Divide both sides by 4.9, and that means that the flight time is 10 seconds. Okay, same problem, find the range of the rock. So recall that x of t is 49 root 3t. I don't need y of t for this problem because the range that I'm talking about here is how far horizontally that it goes. I remember that the flight time is 10 seconds, so the range is going to be how far horizontally it goes in 10 seconds, which is 49 root 3 times 10. This is in meters per second, that's in seconds. So I get 490 root 3. The seconds cancel, and I'm left with meters. Now you'll notice I'm a little bit not perfect with putting in the units. I don't usually like putting them in as I work the problem. Sometimes I would confuse them for variables. But I'll write them in here so we can see that it does work out. So this was in meters per second. This was in seconds. Those units cancel. We're left with a length unit, meters, which is good because the range is a length. Okay, find the maximum height. So now, for this one, I need to use y of t, which was negative 4.9t squared plus 49t. And I need to find when it's maximum, and so I'll do the first derivative, y prime of t, which is negative 9.8t plus 49. And set this equal to 0. It will be defined everywhere, so I don't get any critical points from undefined, but set equal to 0. So 0 equals negative 9.8t plus 49. Subtract 49. Divide by negative 9.8, and I get that t is equal to 5 seconds. And now I use this in that to find the height. So maximum height is going to be the height at this time, which will be negative 4.9 multiplied by 5 squared plus 49 multiplied by 5. Okay. 5 squared is 25, so I get negative 4.9 times 25. Let's see, 49 times 5, well, 50 times 5 is 250, so this will be 245. Let me bring this up here. 4.9 times 25, well, 5 times 25 will be 125, minus 0.1 times 25, so this will be negative 122.5 plus 245. And when I add these up, I'll end up with, make sure it's correctly, 122 22.5 meters. Okay, one final thing, find the ending speed of the rock. Well, we recall that, and I'm going to need both of these, x of t is 49 root 3 t, and y of t is negative 4.9 t squared plus 49 t. Also recall that the flight time, so the ending time, was 10 seconds from the first problems. And in here, I need the velocity. So velocities are the derivatives of the location. X prime of t, which is the x velocity, will be just 49 root 3. Y prime of t, the derivative of this, will be negative 9.8 t plus 49. I evaluate these at 10. So x prime of 10, well, this is a constant function. It's just going to be 49 root 3. Y prime of 10 is going to be negative 98 plus 49, which will be negative 49. And finally, the ending speed. So I'll say that's the final velocity, magnitude of that, will be the square root of 49 root 3 squared plus negative 49 squared. And when I work this out, I actually end up getting 98 meters per second again. So it started at 98 meters per second going up and ended at 98 meters per second coming down. And that shouldn't be surprising here because there's no air resistance to take energy off of it. And these 2 points in this problem are at the same height. So what kinetic energy it loses on its way up as it's slowing down, it regains the exact same amount coming back down. So we end up with the exact same speed. I hope that helped out. Comment below if you have any questions. And I'll move on to some more things with parametric equations.